All right, yeah, so I'm Ryan Mahoney. I work in the same group as Josh Kearns and Scott Summers. We're doing a lot of adsorption type research with biochars. We're getting into sanitation with this new grant I'll go into, but that's my background in environmental engineering and things like that. So, just an overview. I'll first give you a little background on the main project that I spend my time on, and then go into background about ammonia and urine and things like that, my experimental methods and results, and then some figuring out some applications. Maybe people can walk away with something, some applicable information, and then other stuff that are related to biochar that are going on with the project. So the sanitation side of things. I'm glad I'm not the first person to bring up toilets in this conference. We have a little bit of background from the 1800s talking about sanitation, but even today there's a big crisis. 1.1 billion people are still openly defecating. The MDG targets aren't being met, and it's a real big problem in the world. So the approaches, especially in urban areas, have been problematic so far. Dry pit latrines, these ventilated improved pit latrines are usually things that people will dig themselves or try to find a place for. But in urban areas where people are just in such high concentrations, these have problems with filling very quickly and difficult to remove the waste, and transportation being an issue. And then obviously our unsustainable practices related to waste treatment in the Western world. I like the comment, the irresistible flush. People just seem to like to just wash it away and try to forget about it, but someone's got to deal with it at some point along the line. So we're trying to look at better ways of doing that. And of course, composting toilets have similar challenges in urban areas. So from our standpoint, from the Gates Foundation has been running this Reinvent the Toilet challenge. So we won a grant from them about a year ago. And this is kind of like the general sanitation value chain, groups call it. A lot of people in water and sanitation look at ways to capture the waste in a toilet, store it, transport it, and treat it so that it can be reused. So, and then the basic challenge, the big, tough, difficult part related to the Gates Foundation Reinvent the Toilet program is trying to take that and condense it down into one on-site unit that can capture, store, and treat the waste to the point where it can be reused in various valuable ways. So that's what I'm working on with this project. Our idea, we're one of 16 teams out there, we're basically taking mirrors, concentrating solar light so that it's hot, and transmitting it to a reactor that heats up the separated fecal waste that basically dewaters it, and then you can bring it up to temperature and make it into biochar from the solar power. It's kind of like along the lines if you ever burned ants with a magnifying glass or something like that, concentrating light so that it's super hot. And that's just kind of the background that I'm working with. So we're diverting urine so that it doesn't have to go in the same place. And it's also, we've talked about all the nutrients that you find in urine, the fact that it's sterile, it's much less pathogen concern when not mixed with the fecal side of things, and it's simpler to separate it at the source, and then rather than mixing it and trying to separate them afterwards, because then you get a lot of cross-contamination. This is just a urine diverting squat plate I'm sure you've seen around, and hopefully you've all made donations outside. A little more background on the urine. So what is urine? It's super concentrated nutrients and salts and a little bit of organics. This is just some information, a table giving you some of the parameters based around fresh urine when it first comes out of you, and then stored urine after some amount of time. The main thing that I was concerned with this study was the fate of the nitrogen. So when it initially comes out, it comes out in the form of urea, which is organic nitrogen. But this doesn't last too long, as any kind of biogrowth will break it down pretty quickly. In most systems, in a matter of hours, all the way over to ammonia. So we show this reaction going on at the top. Other compounds, this also coincides with the change in pH, which you can see at the bottom of the table. There's pH increases to 9 over the course of this reaction. The urea goes way down. Other things are precipitating, like calcium, magnesium, and phosphate. So with the pH reaction, these precipitate, and usually that's limited by magnesium. As you can see, it's totally consumed in the final storage of the urine. So this is a little bit more in-depth on the reactions going on. Urease basically is the catalyst in the reaction that converts the urea to ammonia. And urease basically released by many microbes just to convert the urea into something they can use better. And so that happens pretty quick. And then what happens when you have ammonia, ammonium, the pH plays a big role. The pK is at 9.2, and what that basically means is that at a pH of 9.2, the species will be 50% each. So they'll be equal. So and then if you go in one direction, as you can see on the graph here, if you go to a higher pH, ammonia is much more prevalent. Lower pH, the ammonium will be more prevalent. So, and the pH of urine, stored urine, just happens to be right around that pKa, conveniently enough. So it makes our experiments a little bit more complicated. So when why are we trying to work with it with biochar? The potential exists to capture these nutrients in biochar, as we talked about, a lot of sorption activities. There's just a high concentration of ammonia in the urine, so it creates an added value for the biochar. It can address some odor concerns, and it can, be part of a total nutrient recovery solution. And as I said before, these can become contaminants in typical wastewater systems, so we want to try to get them. And moving into some of the literature that's been out there, there's been a few studies on absorption of ammonia. Basically, they're all kind of under slightly differing conditions, whether it be gas phase sorption in soils, which is an important part of trying to mitigate climate change and other problems with having ammonia in drinking water and forming chlorines, and avoiding volatilization and loss of ammonia in general. So we're dealing with a slightly different application. So this is the carbon use rate is what I refer to it as. This is an important number you guys can keep track of throughout here. This is the mass of nitrogen per gram of char that you can sorb onto the surface of the char. So I'll be talking about this use rate throughout the capacity of the carbon itself. And as you can see in the previous studies, it's been highly variable based on the study conditions and things like that. And us needing, to do our own evaluation of this stuff is related to the super high ammonia concentrations in stored urine, high salt content, a lot of other competing constituents, and pH effects and buffering capacity going on. So moving into how we're doing this evaluation, we needed to have urine. So we had some debate about doing the real stuff. We were involved mixing a lot of things, and people got nervous about spilling it somewhere. And so we ended up having to use the synthetic recipe that a group in Europe has been working with extensively and developed. So it's designed to be basically a surrogate for stored urine. And so we made this up and used it for batch and column studies. Batch studies were used to find the overall capacity at equilibrium under these conditions of ammonia and biochar. We ran a kinetic study at the beginning just to figure out how long the batch studies had to be to make sure that they had reached steady state, and then dose response experiments to see how much we can remove from the urine and sorb onto the biochar. So these are a variety of the biochars we used. A lot of it's similar methods that you might have seen Josh present on, but if you have more questions about that, you can talk to me. And the batch studies conducted in 50 milliliter centrifuge tubes, basically thrown in this tumbler with biochar, which has been sieved to a low particle size, and mixed in this tumbler for 24 hours was the time we found to be appropriate, just to ensure complete mixing and everything's all good. And then then measured for the pH and other things we were controlling for. And then, so this is the results from the kinetic study, actually, just to show 24 hours was an appropriate sampling time, and we didn't want to. We want to make sure we're at steady state, so we ran it out a little ways. Selecting the chars, we always use activated carbon for these types of experiments, just to give a baseline and try to see a comparison of an industrially produced product. The other stuff is from a few chars from gasifiers, rice husk, pine, at a few different gasifier conditions, different draft and temperature conditions. And then retort, basically chars made in furnaces at different temperatures from different feedstocks, just to compare the difference in char generation temperatures and the conditions and the feedstock. And moving into some of our results, now this is a graph showing the ammonia captured on the left. Usually I do removal, usually I do dose response, but I'm trying to capture the urine in the char. So I'm plotting actually the amount that was taken out of urine solution and swapped to the char, and then the char dose at the bottom. This is the amount of char needed to make that removal. And it is like a spit out of a bunch of data you guys can all look at. Basically, this is all the different chars at different concentrations, and they kind of fall on top of each other in a lot of ways. There wasn't a clear, we expected some orders of magnitude of some differences maybe, but they're all performing around the same. So with similar 3 to 5 milligrams of nitrogen per gram of char for the capacities. So, this is just not a whole lot of variability from one char to another. So we were thinking this is related to just the overall really high concentration of ammonia in the liquid solution that's driving it to these sites. There was some pH changes. I'm glad to see Rachel was on the same page with just pH being a really important factor. So this is something that we looked into a little bit more. But as you can see, things like surface area is not a player here. We got all the way from 1 chars made from the fecal sludge that we collect, and to the powdered activated carbon 1 to 700, and these all performed fairly comparable. So that's the specific sorption mechanism does not seem to be likely. But we did run these at different pHs, changing the pH of the urine. I just added some alkaline materials to change the pH of the urine to 10.3. And you can see that, first of all, we're a little bit higher up in terms of our removals at the same doses, and then we can kind of tease out bamboo at a low temperature bamboo as being a little bit better than some of the other chars. So that was good to see a little bit of variability once we get some removals up. This is just a comparison of different. This is the fecal sludge char for 300 below temperature at 9.3 pH, and then comparing it to the 10.3. We can see that at a pH of 10.3, we got better uptake into the char. And this goes for every char that we compared, that we did these experiments with. So this T-lead pine, and once again about 20–25% better capture of the ammonia in these conditions. So based on this, we kind of deduced that it was likely that ammonia is preferably removed, since that's much more abundant at a higher pH. At 10.3, about 90% of the total ammonium is in the form of ammonia. So we're thinking that that's the constituent that's better removed. The higher pH also showed us some differences in chars, like I showed, and we also ran one at 8.3, and you can see that the removals at lower pHs weren't any better. So we're definitely confirming that higher pHs of urine are better for removal. So confirming some of this related to ammonia absorption. Now moving on into a column, we like to run columns as well, just because you're not always sure how it's going to transfer from a batch to the column. So running bamboo at 350 C, this is the char we used, with an empty bed contact time of 19 minutes, and with the synthetic urine at the higher pH to get a little bit better removal. we got this breakthrough curve, or actually it's the opposite of a breakthrough curve, since we're measuring how much is captured in the urine. And you can basically, we got pretty quickly it started not catching all of the char, but we can get the cumulative amount of ammonia. We took out a solution and found that the cumulative capacity to be around 6 milligrams per gram, which was comparable to the batch studies that were directly related to that. So what could this mean? There's a lot of other studies going on that look at bioavailability of nutrients that are absorbed that have some favorable results. We got a sense of the capacity that we think that the char has and that different chars have. Not a ton of variability in there, but certainly it can affect things. And then looking at kind of applying it to, when you have a certain nitrogen fertilizer requirement. I'm not, I'm an engineer, so I'm just dabbling and running some numbers with this stuff, but it's at 6 milligrams of nitrogen per gram, you're looking at, if you need 2 kilograms, the example shown at the bottom right, if you need 20 kilograms of nitrogen per hectare, you're looking at adding 3.3 tons per hectare of char that will satisfy 100% of that nitrogen requirement, depending on, once again, the variability that other people are doing work on. And so the char can satisfy the fertilizer requirements in this way. Just encouraging, interesting results. So just some conclusions. We're getting a good amount of removal. It's pretty difficult to get all of the nitrogen out of the urine, as you saw from the column experiment. It's just the amount of nutrients in urine just consume the char very quickly, all types of char. So in order to remove, on a quick calculation, just 1 liter of urine, all the ammonia from 1 liter of urine, you need about 5 liters of char, depending on your char densities and things like that. So it's just a lot of nutrients that we're trying to get out. So other conclusions is that just I think I didn't put in our pH data, but the pH for the low temperature bamboo, which we found to be the best, was the best. We actually had the lowest pH as well, so that also correlates with some of the work Rachel was showing. And other than that, I wanted to go into a few other biochar things just to throw them out there, that other applications related to toilets. We're looking at quantifying odor suppressions from a urine stream, from a stored urine situation. A lot of the Gates Reinvent the Toilet teams are looking at trying to use char to mitigate odors, and a lot of them are diverting urine, so issues with smells. We're going to run more kind of robust studies about volatilization and suppressing it in the gas phase. And we're interested in input from other people who might have more experience with this. And also from an odor perspective of drying human waste. It's a pretty smelly ordeal, which I can say from experience. And we did some just studies where we cleaned up a gas stream from a drying phase and measured the hydrogen sulfide breakthrough. We get some preliminary results showing that this is a forced draft pine char that's able to remove below detection limits for hydrogen sulfide, which is also an interesting application for biochar. So with that, we're just looking at to improve and refine our results and studies related to recovering nutrients, and researching biogrowth in a urine biochar column scenario is definitely going to affect things, and trying to incorporate this stuff into business models, or learn more from you, from soils people and agricultural people like you. So it's been a very educational conference for me from that standpoint. And yeah, so I just want to acknowledge the rest of the team, Josh and Dr. Summers, for advising all this work, and some of the people that have helped us out with getting different chars and evaluating them. And I guess thanks a lot for having me.
Oh, I knew this question was coming. introduce yourself, because you got to draw the connection here.
Sure. Abe Noe Hayes, Richard Institute. My question is about the pH of the urine. The elevated pH is due to the ammonia in the urine. When you are stripping the ammonia out into biochar, I assume that the pH is dropping in the urine. Did you measure pH in your batch tests after the ammonia had been extracted? What did you find?
We did, and most of the pH change was actually was negligible, except for that low temperature bamboo that really drove down the pH from like 10.3, to like 9.5 at some of the higher doses. So and I think that's probably a factor into being really acidic, the most acidic char that we had, and having some interactions with the urine to bring down the pH.
So for those of you that don't know, Abe is the one who's responsible for having brought the urine collecting toilet, and they're doing some really interesting stuff up in Brattleboro, where they're asking community members to contribute urine, that they're using a solar dryer to pasteurizer, and then they're putting it on the fields right up there in Vermont. So I knew you'd have a question. Anyway.
Yeah, we've been talking.
I'm sure.
Yeah.
Go ahead. Could you say again the volume of char it took to take up 1 liter of urine?
So I didn't actually do a test based on this, but based on the amount, the amount of uptake of nitrogen that I measured in the various batch experiments, in order to get complete removal, you would need like that 5 liters of char that I mentioned.
And is that up to 300 grams per liter?
That's the density that I used in that just back of the envelope calculation. It's just a lot of nitrogen to remove, and a filter certainly isn't doing that for very long. But you can get a lot of it, get a lot of good stuff out of it. Yeah.
Yeah. Sorry. I mean, your data suggests that it's physical adsorption of the uncharged molecule, whereas the talk that was just given before really suggested an ion exchange mechanism for the ammonium. So it's obvious there's several mechanisms operating simultaneously over a very broad range of pH.
Yeah.
But actually, what point I did want to raise was a little different. The artificial urine you used didn't seem to have magnesium or calcium or phosphate. And in real urine, you precipitate out struvite, which is magnesium ammonium phosphate. And that, which is a powerful fertilizer all by itself.
Yeah, and so
you need the real thing, in other words.
Well, what happened is that there's the research organization that we work with, and have gotten some of this data from, has a variety of different recipes for urine, and the one we used was stored urine. So looking at after that precipitation occurs, after that change, those initial reactions, and like the change from urea to ammonia, and the pH change and the precipitation. Basically, you're considering them non-actors in a filter scenario. If they're settling to the bottom, then they're not. We didn't consider them in our experiment as flowing through some kind of filter. But in a biochar urinal, where it's just sitting in there, it's definitely going to be precipitating.
If you store urine, you get beautiful crystals of struvite forming.
Oh yeah, it's at the bottom there. We got it.
I wanted to add something, and maybe Rachel will have something to say about this. Well, we started to suspect that the actual mechanism, not being really an ion exchange mechanism, but like a nucleophilic substitution mechanism, where the lone pair electrons on the nitrogen on the ammonium attack a carboxyl carbon and kick off an OH and bond that way. So, and I think that's maybe Rachel will have something to say about that, but I think that's why there's some kind of confounding effects when you're tracking changes in pH and trying to understand what change in pH is coming from what process. And actually, I have a follow-up question. How did you minimize volatilization losses when you were pushing the pH up to create more ammonia?
Well, when we're pushing the pH up, we actually did get volatilization, but we controlled. So it's basically kind of became a little bit more diluted than the other recipes we've been working with. I think it was like we lost like 40% to volatilization, but then controlling for that when we do our controls and things like that, we're still looking at a percent basis. So yeah, there was definitely some volatilization. And yeah, from the absorption standpoint, I don't think we think it's a physical absorption relationship, just because those surface areas were not a factor in just a wide variety of different surface areas. So yeah, acid-base reactions and pH related relationships are definitely in play. But
I mean, yeah, to respond, I've seen some papers that propose different mechanisms, but I don't think we know, and I'm looking for more physical and chemical characterizations that could give us better ideas of what's actually going on here.
Matt?
Just one quick comment on the surface areas, and I'm sure if you wasn't here, probably
oh yeah,
stand up and scream about PET or something. But I will say be very careful with PET measurements. I've done them myself. I've had jars that give me less than 1 surface area by nitrogen, and I run CO2 absorption on them, and I get surface areas in the range of 75.
yeah.
So it may be something to consider that you're simply seeing really small pores that are getting screwed up at that 77 Kelvin.
Mm-hmm. And I think hopefully we're not taking kind of the BET stuff for gospel at all. So from a course standpoint, it's not 700 if it's coming out as really low. But but I appreciate you can't tease out some of those lower differences. But yeah, that's a good point.
Anyone else? Last chance? Well, thanks a lot, Ryan.
Thank you.
And